Matt, Tyler,
Hello, hello.
Whoa.
you're in your car.
Yeah, I'm here in Geneseo.
Oh, excellent. Didn't have enough place to go. Couldn't find a desk anywhere?
Oh no, so I'm here for testing, but then I just learned that's because my first test hasn't come out yet. They weren't going to test me, so I'm kind of.
I see. So you drove to Geneseo for nothing. That's sad.
And now I'm barred from any building.
I see. That sucks. So, all right, class from car today. It works. Is that a new haircut, Sarah?
A couple weeks ago.
I'm sorry for not noticing earlier in the week. It looks nice.
I'm back on campus though, so that's
Yeah.
nice. Been back for like not long. Haven't unpacked anything yet, but
welcome. Hi, Bisma. Welcome, Dano. Welcome, Gabe. Welcome, Morgan. 2, 3, 4, 5, 6, 7, 8. Kind of looks like Bisma's in the union. Are you in the union, Bisma? She had no idea what I was saying. Or
the world may never know.
we may never know. Looks like you're in the union, Bisma. Are you in the union?
Yes,
excellent. You should let Tyler in. He's stuck in his car because he can't get in anywhere.
Oh, no.
I'm just kidding. It's fine. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's Connor. Welcome, Alex. 1, 12, we're at 11. I'm missing 1 or 2. Oh, and there's Miles. Hey, Miles, welcome. Welcome, Miles. Good to see you. All right.
Computer has not been working well with me these past few days. That's all.
I'm sorry. That's too bad. But glad you're here. Excellent. Well, I don't know if we have. Oh shoot! You know what I totally forgot to do was look at my Astrobytes article this morning. I get a fail for the day. Let's do that Monday. So read that article or reread it before Monday, and we'll do it Monday morning. Apologies. Maybe we'll do it in person. Dang. I knew there was something I was supposed to be doing this morning, and I did not do that. Oh, well. Cool. All right. Let's just get straight back to the astrophysics. I don't think there's any announcements. Kappa's up. That's due next week. And we'll talk about Astrobytes next week. Cool. All right. It's been one of those weeks. I'm hopeful we're back next week, but I'm not confident, right? The number of cases on the Geneseo dashboard is disturbingly high. And I've heard rumors that if it climbs significantly higher than it is, that there's going to be like a 2-week pause. So just be aware and prepared for that. It may be coming in the next few days. We'll see. All right. Hope we don't have to do that, but we'll deal with it if it happens. Okay, so where were we? We were talking about the magnitude system. Oh no. Oh, that worked. Yay. Okay, so we wrote down the equation for the magnitude scale, but it's useful to sort of see it here also. So this is the entire magnitude scale. Remember, the weirdness about the scale is that, one, it's a log scale, and 2 is backwards. The log scale actually comes in handy because it means we can categorize the brightness of every single object in the sky, from the brightest thing in the sky, the sun, all the way down to the very faintest stars that the Hubble Space Telescope takes a week to be able to detect, in a scale that only spans about 55 numbers, right? The brightest thing in the sky is the sun. And here it is, the sun's brightness in the sky on the magnitude scale is negative 26.7. The full moon, the brightest the moon gets, is about negative 12.6. The planets are brighter. They have most, well, not all of them, but many of them have negative magnitudes. Of course, those change as we're orbiting the sun and they're orbiting the sun. We're at different distances from them. So depending on how close we happen to be, they will be at different magnitudes and different brightnesses. Venus is the brightest planet when it gets to be its brightest at negative 4.4. The stars begin at negative 1.4. This is the brightest star in the sky. Sirius, negative 1.44. Vega, one of the brightest stars in the sky, is, remember, the definition of this scale, and it's right at 0. It's defined to be magnitude 0. So again, there's a handful of stars that are brighter than Vega, including Sirius, but Vega sort of sets the 0 point of the scale right at 0. Every single star that you can see in the sky falls between Sirius at negative 1.4 and about magnitude 6. These are all of the stars that you can see in the sky. And even 6 is pushing it. You have to be at a pretty dark, a very dark site. That is sort of the limit at the darkest sites of the stars that you can see in the sky. If you're not at a very dark site, if you're on Geneseo's campus, the faint limit is going to be quite a bit brighter than that, because the sky background is going to be bright enough that you won't be able to make out some of those fainter stars. And if you're in the middle of Manhattan, you know, it's going to be more like 2, magnitude 2 cutoff. So it depends on how bright the sky is, how faint you can actually see. But 6.0 is about the limit even at the darkest sites. So that again harkens back to Hipparchus's scale, right? He put all of the magnitude 1 stars in the brightest stars in the rank 1, and the rank 2 were the next brightest stars, and the rank 3 were the next brightest stars. And so that system of Hipparchus's is kind of preserved in this scale, where the brightest stars are small numbers to 0, even negative, and the faintest stars we can see are in the 5 to 6 range. Going fainter than that, even with binoculars, you can't see much past 10. Pluto is down here at 15th magnitude. When we go to a telescope at Kitt Peak and are taking data with our 36-inch telescope, primary mirror is 36 inches in diameter, 3 feet across, we are seeing stars that are in the 10 to 20 range, right? We can't see much fainter, even with our 36-inch telescope, than about magnitude 20. With larger telescopes and with space-based telescopes, you can see fainter than that, but it takes a lot. And down at plus 30, you're pretty much at the faintest that anybody can see. So that's it. From negative 26 to plus 30 is the entire magnitude scale of everything that we can possibly see in the sky. So that's useful to have in the back of your head as you're dealing with these magnitudes. This is where various things fall on the pattern. All right, let's do some more math, because math is fun. Remind you what the equation is. I like it thicker than that. M1 minus M2 equals negative 2.5 times the log of B1 over B2. This is the magnitude equation that we wrote down last time. And it's weird because, again, it's only characterized as a difference. This negative sign codifies it being backwards, where the brighter the star, the smaller the magnitude. And of course, there's a log base 10 here to make things go. So let's try this out. What if we had 2 stars whose brightness ratio was 100? So let's say B1 is 100 times brighter than B2. What is that going to mean for a magnitude? So let's say for B1 over B2 equals 100. What is that going to give us? Well, this is going to be pretty simple. negative 2.5 times the log of 100. Log of 100, this is log base 10, so it's really easy. Log of 100 is just 2. And negative 2.5 times 2 is negative 5. So this is a good rule of thumb, right? If you have a magnitude difference of 5, that corresponds to a brightness ratio of 100. That's the rule of thumb to have in the back of your head. If a star is 100 times brighter than another star, its magnitude will be 5 less than that other star. So we can actually codify this now, right? This whole scale, every single one of these steps of 5 is a brightness ratio of 100. These stars at 10 are 100 times brighter than these stars at 15. These stars at 5 are 100 times brighter than these stars at 10. And Vega is 100 times brighter than those stars at +5. Okay. By the way, if you look in the textbook for the magnitude formula, it's going to be slightly different. The book has this ratio, this formula, B1 over B2 equals 100 raised to the M1 minus M2 over 5. Oops, that's not a 5. That's not a 2, it's a 5. These two equations are equivalent, but and you're welcome to use either one. They'll both work. I prefer the log equations, just maybe because I'm used to it. But I think I understand logs better than I do 100 raised to powers of things personally. So if this other one works better for you, then that's fine. Just to remind you from last time, these B's, actually the book uses F's for these, capital F's, but it means the same thing. These are radiant fluxes. These are brightnesses. B's have units of, the unit on B is watts per square meter, right? It's energy per second passing through some aperture. That is how we define brightness. This is a normal, sane way to measure brightness. Okay, how about some other terminology? Luminosity, probably a term you've run across before. This is the total emitted energy per unit time by an object. So it, of course, has units of luminosity, has units of joules per second or watts. So for instance, the luminosity of the sun, and by the way, I haven't defined this yet, but this is typical nomenclature. A circle with a dot in the middle of it is the shorthand way of writing the sun. So if I say L sub circle dot, I mean the luminosity of the sun. That is 3.84 times 10 to the 26 watts. The sun is a 3.84 times 10 to the 26 watt light bulb. And of course, it's radiating that energy away roughly uniformly in all directions. How are B and L related? B, the brightness that we see from an object, is the luminosity divided by 4 pi times the distance to that object squared, right? This is, if you remember back to Analyte 3, brightness equals power times area. I should stop talking because I'm not remembering exactly how that works. Doesn't matter. So remember how this works. If you have an object at the center of your thing and it's radiating that energy away uniformly in all directions, then by the time you get to be some distance d away, that energy will be spread over a sphere whose radius is the distance that you are to that source. And so 4 pi d squared is simply the surface area of a sphere with radius d, and that is how much you have spread that energy over surface area wise to get a brightness at a particular distance. This is the 1 over r squared law of light. Double the distance to a source, you will decrease the brightness by a factor of 4. Okay. Great. Let's go back to magnitudes. Right. So you might think that we would not be silly enough to carry this scale over to luminosities, right? We have this arcane magnitude system for measuring the brightnesses of objects. Surely we would not carry that over and use the same system for measuring luminosities of things. You'd be wrong. We do. So we define, instead of actually using luminosities, right? We don't actually talk about luminosities being 10 to the 26 joules. We have another thing for that, and it's still a magnitude. And this is called the absolute magnitude. Which is to differentiate it from the other magnitudes that we were talking about, which were definitely apparent magnitudes. I didn't say that, but to distinguish them from absolute magnitudes, we use apparent magnitudes. Apparent magnitudes, of course, are the brightness that we see an object to be, right? Is a measure of how bright we see an object. An absolute magnitude is a measure of a star's intrinsic brightness. It's a measure of its luminosity. So a measure of luminosity. So apparent magnitude is dependent on the distance to an object. The absolute magnitude is not. You could take the sun and move it to the other side of the galaxy. Its apparent magnitude would change quite a bit. Its absolute magnitude would not. Its brightness would change a lot, but its luminosity would not. Okay. So this is the definition of an absolute magnitude is this. And from that definition, we'll come up with an equation that we're going to use. The definition of an absolute magnitude is the apparent magnitude that a star would have if it were exactly 10 parsecs away. Does away with all these messy units. Who needs joules and watts and seconds when we have unitless magnitudes? Okay, so if you're just doing, I'll say generic magnitudes, usually we use little m to be apparent magnitude and capital M to be absolute magnitude. The formula is exactly the same. So for absolute magnitudes, the formula is going to look very similar. M1 minus M2, these are capital M's now instead of lowercase m's, equals negative 2.5 times the log of the ratio. Now, instead of the brightnesses, we're going to take a ratio of the luminosities of these two objects. So just like there's a relationship between B and L, though, there must be a relationship between apparent magnitude and absolute magnitude. So let's take a moment and derive that relationship. So let's see, we from the definition of the absolute magnitude, we can make this, we can make this difference. The apparent magnitude, so this is one difference, right? Before we were talking about M1s and M2, we were talking about two different objects. Here, we're talking about the apparent and absolute magnitude of the same object. The apparent magnitude minus its absolute magnitude must be negative 2.5 times the log of its brightness, whoops, its actual brightness divided by its brightness at 10 parsecs away. So let's call this B10 the brightness or the flux that star would have if it were at 10 parsecs, right? That should be, this is the definition of the magnitude, m minus m negative 2.5 log. This B10 is the definition of how the apparent magnitude and the absolute magnitude work. So what is B over B10? We know that the brightness of an object is simply the luminosity divided by 4 pi times its distance squared. And we know that the brightness at 10 parsecs is the luminosity divided by 4 pi times 10 parsecs quantity squared. And the stuff kind of just cancels out now. This is the nice thing, also a nice thing about taking ratios is many times things just go away. So our L over 4 pi go away. We don't care about the luminosity anymore. We're left with this d squared is in the denominator of the numerator, 1 over d squared divided by 1 over 10 parsecs squared, quantity squared. So this is, let's just bring both sides up to the top, 10 parsecs squared over d squared. And that is 10 parsecs over d. I'll do it down here. Quantity squared. So the ratio of the brightness that we actually see from the star to the ratio of the brightness of the star would have at 10 parsecs has to be 10 parsecs divided by d, quantity squared. Okay, let's plug this back into our magnitude equation. Little m minus big M equals negative 2.5 times the log of 10 parsecs over d, quantity squared. Okay, let's do some magic now. If we have some log magic, if we have a quantity inside a log that's taken to a power, we can pull that power out and attach it to being a multiplicative factor instead. So I can take this squared inside the log, move it outside the log, and make it multiply by 2. So this is equal to negative 5 times the log of 10 parsecs over d, and I no longer have to worry about all those squares inside there. I can also flip this ratio and make it d over 10 parsecs by changing the sign here. And I'm going to do that now too. This is plus 5 times the log of d over 10 parsecs. And if I have things that I'm dividing by each other, if I have a ratio inside of a log, I can split that log up, the ratio up, and make it a difference instead. So for instance, I can make this 5 all times the log of, let's keep the parsecs with d over parsecs, minus the log of 10. Again, you need things to be unitless inside of your log. So this is really d over 1 parsecs, and this 10 is now unitless. Everybody followed along with that, okay? I'll assume so, yes. What's the log of 10 though? See if anybody's paying attention.
1.
It's 1. That's right. The log of 10 is just 1. So this is really 5 times the log of d over parsecs minus 1. Let's move the 5 through. I need a new page for this. This is why I don't like single pages. So I have little m minus big M equals 5 times the log of d over parsecs minus 5. And so that is actually the equation that you typically see. 5 log d minus 5. And I'll give that one a little box because it's important. Now I've gotten rid of the parsecs as is usually done here, but you need to know that d is in parsecs. This equation only works when you plug in d in parsecs. This has a name, it's important. It's called the distance modulus equation. And this quantity, little m minus big M, is known as the distance modulus. It is not a distance, but hey, everything else is in magnitude space. Why not make distance in magnitude space as well? In fact, that's basically what this does. M minus M, little m minus big M is a distance modulus, and it is a proxy for distance. The bigger the little m minus big M value, the further away an object is. And in fact, if you go to an astronomy conference and you're looking at posters where they're looking at stars and star clusters and they're measuring distances to things, you will often see it reported a distance modulus instead of an actual distance in parsecs. It's easy enough to move it back to a parsecs, but again, it's a log scale and it can make differences that are many, many orders of magnitude in distance seem more tractable and with smaller numbers. Okay, so you'll need this equation for some of the homework next week. Note that this is a way to get distance, right? If you know, little m you always know. You're always going to be measuring the brightnesses of things. That's an easy thing to get. If you can somehow know what an object's true luminosity is or its true absolute magnitude, that gets you the distance. So this is the method of standard candles. If you know how bright your candle is intrinsically, and you measure how bright it is apparently to your eye or to your telescope, or how much flux it has, that will give you the distance to that object. Okay. On the contrary, if you know the distance to an object, that can give you luminosities as well, and intrinsic brightnesses. And that's how we learn interesting things about objects in the universe. Okay, great. Moving on. Section 3.4, black body radiation. Does anybody remember what a black body is? This is, again, something we covered in Analyte 3 a little bit, and you probably continued it in Analyte 4, I'm guessing, a little bit, hopefully.
Is it an object that perfectly emits and perfectly absorbs all radiation?
That's right. It's a perfect emitter and absorber of radiation. That's exactly right. A black body is a perfect emitter and absorber. It absorbs all incident light. And the only light that comes from it is emitted thermally. Excellent. We talked about these at some level in Analyte 3. There's very interesting stories about how this equation was derived. But if you have a perfect black body radiator, its spectrum, its energy production spectrum. So we're all emitting. Let's just go back and summarize and recap what we learned in Analyte 3. Every object with non-zero temperature in the universe, and by that I mean every object in the universe, radiates light. And the more how that light is radiated is characterized solely, if it's a black body, by the temperature of that particular object. And so you can characterize how an object will emit light and at what wavelengths and what frequencies by the Planck curve. And how this Planck curve was derived is very interesting, of course, to the foundations of quantum mechanics, but that's not what this class is about. So let's just write it down. So B sub lambda sub T. So this is the black body radiation Planck function curve in wavelength space as a function of temperature. And so this is 2h times c squared over the lambda to the 5th times 1 over e to the hc over lambda kt minus 1, where, recall, h is Planck's constant, c is the speed of light, and k is Boltzmann's constant. I'm not going to bother to write down the numbers. You can look them up. You probably know them off the top of your head anyway. Maybe with the exception of Boltzmann's constant, but you can look it up. Oh, I'll write it down. I'll write down Boltzmann's constant. I've got it right here. 1.381 times 10 to the negative 23. And that's joules per Kelvin. This is a constant for turning temperature into energy, which is basically what's happening here. Cool. So this B lambda thing is weird. It's a spectral energy distribution function. So let's recall what B lambda is. It's energy per unit time per unit area per unit wavelength, and this is the one that usually gets people, per unit steradian. Anybody know what steradians measure?
Solid angle.
It's solid angle. That's a two-dimensional angular measure. Exactly right. Do the units work? Let's go back and look at this thing. We need, obviously, the units inside this exponent to cancel out. Let's just see. We've got hc on top and lambda kt on the bottom. Hc is units of joules times seconds times meters per second, which gives you joules times meters. And lambda kt gives you meters, which is the lambda. K is joules per Kelvin, and T is Kelvin. Kelvins go away, and you've got joules meters. So that's good. The exponent inside, the units inside that exponent cancel out. They have to. You can't have units inside an exponent. That just wouldn't do. What about on the outside? On the outside, we've got the 2 doesn't matter. We've got hc squared over lambda to the 5th. What's that going to give us? What are the units on hc squared over lambda to the 5th? Well, h is joules seconds. C squared is meters squared per second squared, all over meters to the 5th power. What are we going to get here? We're going to get joules per second times meters cubed. And that's exactly what we want. We want energy, joules per unit time, per unit area, that's 2 of these meters, per unit wavelength, that's another 1 of these meters. And steradian is in here, but it's kind of like radians, and it kind of goes away and you don't even know what's there, but it's in there. Okay, cool. What does it look like? You've seen this before, but let's do a quick crude drawing of what this looks like. This is wavelength, and this is B. You've got something that looks kind of like this, right? So you've got 2 parts of this, right? There is a 1 over lambda to the 5th thing here outside, and then you've got this exponent in the so again, this is B as a function of wavelength. So you've got e to the 1 over lambda in the denominator. So this is actually exponential growth. So this is the exponential part of it. And then eventually when lambda gets big enough, the 1 over lambda to the 5th takes over and kills you on the other side. So these are rapid rises and rapid declines. This is not a small function of wavelength on either direction. It's exponential growth followed by 1 over lambda to the 5th decline. So this is important. As you increase temperature, so this is just at a single temperature, right? If you change the temperature, B goes up at all wavelengths. And the wavelength of peak emission gets shorter. We'll call this lambda max. Okay, here is the textbook's view of this. Again, this is B lambda T as a function of wavelength for 3 different black body temperatures. And you can see both of those things that I described below happening here. Here is a 4,000 Kelvin black body. It's peaking somewhere over here near, I don't know, 700 nanometers or so. Here is the sun. The sun is 5777 K. It is brighter than this 4,000 Kelvin star at all wavelengths, right? But the peak wavelength, the wavelength at which it reaches most of its energy, shifts towards shorter wavelengths. And here's a 7,000 Kelvin star. This isn't that much higher in temperature, right? Higher, you know, we haven't even doubled it in going from 4,000 to 7,000. Look how much higher this peak is over here. Brighter at all wavelengths, and the peak continues to shift towards shorter wavelengths. We're going to do some mathematical exercises, but I want to show you this is a black body radiator with a temperature of 5777 K. The sun is not a perfect black body. It does not absorb every single photon that hits it, and it does not emit only thermal radiation. So if you want to look at the actual solar spectrum, this is the actual solar spectrum. And green is a black body curve of 5777 Kelvin object. It is a perfect black body. You can see there's some interesting differences here. First of all, the peak isn't quite in the exact same place. And second of all, there's all these crazy absorption lines. How are those formed? Where do they come from? Why are they important? What do they tell us? That's going to be a focus of a different part of this class. But we will be studying in detail why the solar spectrum looks the way it does and what information we can glean from it and how it's different from other stars of other temperatures. These are interesting things. Okay, with the last 10 minutes I have today, I want to give you some tools in Mathematica and show you how we can use Mathematica to do some interesting calculations and visualizations with this particular law. So pull open your Mathematica sheet. This is going to be a little bit tricky. You're going to have to both see what I'm doing and probably have your Mathematica sheet open so that you can be following along. I'm recording this, of course. If you miss something, you can always go back and watch it later. But if you are totally lost and missing something, you can stop me. I will slow down and we'll do that. Okay. So, ooh, there's a chat. I totally missed it. -5. Did I get something wrong, Hunter?
No, this was when you were doing the very first magnitude calculation.
Oh, okay, cool. If I do get something wrong, and it's going to happen, please stop me and let me know. Awesome. Okay, so let me share my. There's my Mathematica sheet. Oh, here it is. Let me open up a new one. Okay, here we go. I always start with a clear all global. I was actually just doing some of this stuff before, so it's not gonna, should be messing me up if I don't do that. This is the weird syntax. There should be an easier way to do this, right? To tell Mathematica that you just want to clear all the variables and the caches. Why would it need to be such a crazy combination of random characters? That doesn't make any sense. Come on, Steve Wolfram, get your act together. Anyway, all right. So, but Mathematica is cool because all of this stuff is just built in. Pretty much everything in physics is built in. You just have to know how to use it. So for instance, I can type Planck, PLNCK radiation law, and look at that, it's already being, if I just hit tab now, it'll automatically complete for me. Planck radiation law is a thing. That is that B sub lambda thing that we're just looking at. Now, you're going to have to use, so it takes two inputs. It takes a temperature and it takes a wavelength. And it's going to, among other ways, there's lots of ways to use this, but that's one of them. And it will give, so let's try this. But we have to actually give it a temperature in Kelvin and we actually give it a wavelength in some physical units. So we're going to have to use units here. And the way to use units, a quantity with units, is with the word quantity. So let's say we want to know a black body with a radiation with a temperature of 10,000 Kelvin. We need to tell it 10,000 Kelvin by using the quantity thing, 10,000 kelvins. And again, it will actually suggest a thing, and you can hit tab and it will autocomplete for you. So that's giving it the temperature. We've given it 10,000 Kelvin. We now need to give it a wavelength. So let's say quantity 500 nanometers. That is right in the middle of the visible part of the spectrum. Oh, maybe a little bit short of the middle of the visible part of the spectrum, but it's smack dab in the middle there. I need to close both of those. And if I hit enter now, or shift enter, if I evaluate this thing, it's going to give me a number. Now, that of course is a crazy number. Nobody would ever want it printed that way. But if you give Mathematica whole numbers, it will do things symbolically and in ratio form as much as it can. And so this is, if we just make this 10,000 point, it will give us a normal number. That's a useful Mathematica trick too. If it's giving you ratios and you don't want ratios, just make one of your numbers a decimal and it will work just fine. So 10 to the 14 watts per cubic meters per steradian. Again, it's keeping the steradians in here. So this is useful, right? It's evaluated that B sub lambda quantity at a particular temperature and a particular wavelength. Now, normally we want to plot this, so that can be done also. If we do, I'm going to copy this over here, the Planck radiation law. Actually, what am I going to do? Oh, yep, that's what I'm going to do. And instead of doing a single wavelength, I can type in quotes, spectral plot. And then hit enter. Hey, it gives me a spectrum plot, which looks very similar to the one that we just saw before. Now you can see, instead of just evaluating this thing at a single wavelength, we've actually plotted it over the sort of typical range. I can plot more than one of these at once if I want to. I can call this P1. I can copy this whole thing and say P2 equals some smaller, let's say 5,000 kelvins. It looks exactly the same, but you'll notice the scale is different, right? We've got 10 to the 14 here and 10 to the 12 down here. It doesn't look like, oh, even this scale is different, right? This one goes out to 2.5. This one goes out to 5 times 10 to the negative 6. So if we want to show those two together, I can do a show with a capital S, P1 comma P2, and it will plot those both on the same axis. This is crazy. Look at how much doubling the temperature has changed this power output. As you know, maybe you remember from, I can't remember whose law it is now, but power goes as t to the 4th power, right? And the power is the total integral under this curve. And so clearly, doubling the temperature raises the power by a substantial amount. It's in fact a factor of 16. If we make this, I don't know, 8,000 instead, this is going to be a little bit more reasonable, and you can actually see some differences between those two. It's still hard to pick out, but this peak happens at a slightly longer wavelength than that peak. Cool. In fact, that's probably what we want to know next. Where do these curves actually peak? Let's see if we can use Mathematica to find out. You can't actually, no, so the way you would do that, of course, is to take a derivative and set it equal to 0. But I've tried and I couldn't get Mathematica to take a derivative of this thing. So you have to be a little bit more clever about how we're going to do it. One way you can do it is with a find maximum command. So this gets messy. Write this down or follow along because this gets messy. We need quantity magnitude. I misspelled quantity. Quantity magnitude. Quantity magnitude will give you just the magnitude of a quantity. So Planck radiation law. Oops. Quantity. So let's just break down what I'm doing. I haven't been able to figure out how to get Mathematica to do things like take derivatives or find maximums of things that have units. And so quantity magnitude is a way to return the value of an object of a function without the units being attached to it. So I'm going to do exactly what I've done up here with Planck radiation law with units, but this quantity magnitude is going to strip the units away so that find maximum can actually do the thing without units being attached. So quantity, same thing I had before, 10,000 kelvins. Quantity, now this is where it's going to get interesting. Oh, that's not right. It's giving me red. I need a closed bracket there. Quantity. Now, instead of giving it a single wavelength, I need to give it a whole range of wavelengths so that it will find the maximum between two things that I'm doing. So I need to make a variable x, nanometers, where x, I'm going to do 3 closed brackets to get all the way out to find maximum, where x is going to be between, let's say, 200 and 500. That should do it. So again, some number, so it's gonna vary x sort of between 200 and 500, or it's just going to look for a maximum in this range, and that should do it. Let's see if we can. Hey, it worked. So it's giving us two things. It's giving us one, the value of the peak, right? You can actually see that here, about a little over 4 times 10 to the 14, and it's giving us the x value or the wavelength at which that actually happens, which is 289 nanometers. This is in meters. This is 289 nanometers. That's cool. We can use Mathematica to figure out where this thing peaks. All right, what if we change the temperature? I'm going to copy this whole thing and paste it down here. And let's do, I don't know, 5,000 kelvins instead. Oh, how interesting. You decrease the temperature by a factor of 2, and what's happened to the peak wavelength?
Doubled.
It's basically doubled. So that's interesting. Let's see if this holds. Let's go to, if that's true, then it should be that if we go to 1000 Kelvin, which is 10 times less than this, then the peak should be 10 times higher. We should get 2897.77 something. Let's see if that works. Boom. We've discovered a law. We've discovered a fundamental law of the universe. And that is that the temperature of an object and the wavelength at which its black body radiation spectrum peak are inversely related to one another. If I were to write this down, I would say lambda equals proportional to one over temperature. And I don't mean just lambda, I mean lambda max. So I'm basically out of time for today, but we will use the full power of Mathematica on Monday to figure out what this proportionality constant is. It's actually not that hard to do. We've already got enough information. We know that lambda max times T is constant, right? That's what this is saying. Lambda max times T is constant. And so once we know that what that proportionality constant is, we're good to go. But you can already calculate it. It's this number times this number. That's going to be the same for all of these. This number times this number, and this number times this number is always the same. All right, so we'll come back and on Monday figure out exactly what that is. All right, and I will remember to do the Astrobytes article. Apologies 100 times over for that misstep. Have a good weekend though, and we'll see you hopefully in person in class in ISC 229 on Monday afternoon. That's all.
Thank you, Doctor.
On Monday.
Good day. Thank you.
Goodbye.